Okay, and this is 0. So once the input is given to a system, we are considering here step input for your understanding. So we are giving the input the step manner, and this particular line point A represents steady state of response X. So when step input is given, so uh, the response of system will increase and it will cross the steady state during its transient phase, and with due course of time this transient phase will die away with time and it will reach a steady state at a particular time ts. Okay, and the peak, let's say the peak the system is achieving at a time period of tp. Okay, and the system is reaching the steady state from its zero value to a time tr. Okay, so, okay, and this, to reach this time tr, the system is completing a quarter cycle of pi by 2, and to reach this time tp the system is completing a half cycle of pi. Likewise, it will be completing the cycle. Okay, the peak value it is reaching, so the distance from the steady state value to the peak value is termed as overshoot. Okay, and the reason at which the system is gaining the second peak, although it's in the opposite direction, is, let's say, consider it as a 2% of steady state. So usually it will be given to you 4%, 5%, 6%, likewise. But here we are, for your understanding, we are considering 2% of steady state. Okay. So this is the response of system with due course of time, giving a step input and a underdamped system. Okay. I hope this graph is clear. Now, in order to evaluate the performance of system, we have to deduce certain uh, values or certain parameters. First, we will be considering the rise time. So the performance is evaluated on the basis of certain terms. The first and foremost term is the rise time, and the rise time is defined as the time to reach steady state from its zero value. Means the time taken by system to reach steady state from its zero value. So this particular term is your rise time, which is denoted by tr. The rise time is also measure that how fast your system is responding. So fast response of the system, okay, or fast response to the input. Okay, how fast system respond to the input. Okay, and also rise time is also time for here the response is oscillating, so time for oscillating response to complete quarter cycle, which is pi by 2. So wtr is equal to pi by 2. So from here you can measure tr, and w is equal to wn upon 1 minus damping factor square. Okay, okay. In few cases you will in few cases it is mentioned that the rise time is the time required by a system to reach a certain value from a certain percentage of steady state. Means, let's say your system is at 10% of steady state and it is reaching 90% of the steady state. So the whatever time it uh, takes to reach a particular state from its previous state is also considered as rise time. Second is your peak time. Okay, so peak time is basically time taken by a system to reach its peak value from the zero value. Okay, from the zero value, or also it is defined as the time required to complete half oscillation. Okay, only half of the cycle means so TP. So WTP is equal to pi. Okay, so TP is equal to pi by omega. Okay, so from here you can measure peak time. Next is your third is your overshoot. So basically it's a maximum amount. Basically it's a measure of maximum amount a system overshoots from its steady state value. So here this is the overshoot. Okay, so time. Okay, time at which a maximum amount by which system can overshoot from its steady state value. So this is the first overshoot. Likewise, this is second, third. So before reaching steady state, a system may go under number of overshoot. It can be one, two, three, four, depending upon the system. Okay. So basically, if you want to consider overshoot, let's say we have to calculate the amplitude of first peak. Okay. So if you consider overshoot response, so x will be equal to E omega n t, E minus damping factor times omega n t, P cos omega t plus Q sin omega t. This we have calculated for a underdamped system in our previous class, plus the steady state component. Okay, so which will be equal to x double s. Okay, so at x is equal to 0, t is equal to 0. Okay, so what you will get, x is equal to p times x double s. So here if you cos 0 is 1, sin 0 is 0, so p plus q times of 0, so that's why the q will be removed at t is equal to 0. That you can understand, I think. Okay, so so basically P will be minus X times double S. Okay, steady state. Okay. So we are considering that overshoot is taking place. The peak is reaching at omega t is equal to pi. Okay. So at you keep the value of omega t there. So what will you get? X t is equal to sorry, omega t is equal to pi. So here you can also replace t by pi by omega and p cos pi plus q sin pi plus. So what you will get? Minus of x damping factor times. Okay. So this particular component is termed as the overshoot. Okay. So the overshoot will be minus x times x steady state times e power damping factor pi omega n by omega. Okay. Now you can replace omega n by 1 by omega times. Okay. Sorry. So your what is your omega? It is omega n times. Omega n is your natural frequency, 1 minus damping factor square. Okay, you keep that value here. So what you will get? E power damping factor. Is it fine? Okay, and the percentage overshoot will be this value times 200. Okay. The fourth important term which used to evaluate the performance of the second order system is your settling time. So settling time is basically the time required by the oscillation to settle down or time required by the oscillation to die away. Okay. So okay. So this is time to response. Okay. Time to response, time taken by a response to reach the steady state. Okay. So it is given by, here we are considering that settling time Ts is reaching at 2% of steady state value. Okay. So same x is equal to omega n p cos omega t plus q times uh, sin omega t plus your steady state value. Okay. At t is equal to 0, p is coming out to be minus of steady state value. Okay, and you are reaching the settling time when your x is equal to zero point 0.0 times of xs. We are considering as 2% of steady state value, so that you can put. Okay, and see here, to reach this time period, this settling time Ts, the system is going through the number of peaks. Okay, if you can see, and these peaks will be are in the multiple of pi. Okay, so it will be it will be a multiple of pi. Okay, so there is a, yeah, when x equal to 0.02, so this is this reach reaching at the cycle in a multiple of pi. Okay, so what will happen here? Zero point 0.0 times of xs, and it will be a multiple of pi, n pi, n pi. So accordingly, uh, you will get p times s. Okay, or, and this particular value is your representing your settling time. That is this particular value. Yeah. So so from here you will get the value of settling time. So wait. Okay. Next is your, so wait. This particular term. Hold on. No, let me correct it. It's, yeah. So this particular here represent the settling time value, uh, where x is equal to 0.02%, 2% of excess. Okay, and it is happening in the multiple of pi, so you will get minus of xs. We are focusing on this particular value. Okay, so your xs will get cancelled. You will get ln 0.02 minus of omega n. Oh, sorry, minus of omega n. Okay, so from here you will get omega here. So from here will be omega n t, which is happening at ts. So ln 0.02 is equal to minus of damping factor into omega n into ts. Okay, so after solving and rearranging it, you will get ts is equal to 4 times of omega n. So this is in the case when you you have settling time at 2% of your steady state value. You can have 3% also, 4%. Okay, depending upon the it will be mentioned for a particular system. So now on the basis of that, let's try to solve some problem. So you consider a system, consider a second order under damped system for which your natural angular frequency is 2 hertz and damp is 1.8 hertz. Okay, so omega is equal to 2 pi f. So omega n is equal to 2 pi of 2 hertz and omega is equal to 2 pi of 1.8. So this is natural and this is in the damped condition. So you have to calculate damping factor, rise time, peak time, percentage overshoot, and settling time. All right. So first, omega is equal to omega n times 1 minus damping factor square. So from here you will get what? 1.8 into 2 times of. So your damping factor will comes out to be 0.44. Okay. Next is your rise time. So rise time is equal to omega tr is equal to pi by 2. Okay. So from here you can calculate 2 pi omega is 1.8 to tr by pi by 2. Okay. So from here you will get tr equal to 0.87. Okay. Likewise, what is the peak time, which is omega tp is equal to pi. Okay. You put the value of omega here 1.8 pi. So tp you will get 1.74 seconds. Next is your percentage overshoot, which is very easy to calculate, which is uh, e power minus pi times damping factor divided by 1 minus damping factor square whole root into 100. So we have calculated damping factor also, which is 0.44, 1 minus 0.44 square into 100. Okay, so from here you can calculate overshoot. It will comes out to be 2%. Next is your settling time. So settling time is equal to 4 upon omega n damping omega n times damping factor. So omega n you have calculated. Okay, so you can 0.44 into 2 point into whatever your frequency is. I think it's 2. So from here you can measure it. Okay, next is your, in few questions you will be asked with number of oscillation. Okay, so number of oscillation will be basically settling time divided by periodic time. So this periodic time is equal to omega n is equal to 2f and t is equal to tp, that is periodic 1 by f. So your tp will be, you keep the value of f here, it will come out to be 2 pi omega. Okay, so and your settling time is, okay. So from here you keep the value of omega n, okay, and you can calculate the number of oscillation will be 1.3. Okay, you can keep this value. Okay, omega n you have calculated, which is this will be 2 here, uh, like 4 times pi, and it is 2 pi will get cancelled. Okay, and you will get the value. Okay, uh, next is there is one more question. So I hope my screen will. So I hope this is visible. So this particular question is on page number 482 of your Walton. Okay. So if you see here, when a voltage of 10 volt is suddenly applied to a moving coil voltmeter, okay, it is observed that a pointer of instrument rises to 11 volt before eventually settling down to 10 volt. So we have to calculate what is the damping factor and number of oscillation the pointer will make before it is within 0.2% of its steady state value. So from here, it should be 2%, okay, not 0.2%. So from here, we have to measure the damping factor and number of oscillation. So let's try to solve this. Okay, so it is asked that the voltage is reaching the value. Uh, Suddenly, when voltage is applied, it is increasing from 10 to 11 volt. Okay, so it is reaching its peak and then finally settling down. So the overshoot percentage will be 11 minus 10 upon 10 into 100, that is 10%. Okay, so 0.1, 10% means 0.1 into percentage overshoot. We will calculate we have the formula with us, pi damping factor minus 1 upon. Okay, so from here you will get minus 2.3 minus, okay, just cancel, and from here you can calculate damping factor as zero point 0.4. So you got the damping factor value. Next is you have to measure the number of oscillation considering 2% of the steady state. So it is very easy. Number of oscillation will be settling time upon periodic time. So settling time upon periodic time, uh, it will comes out to be, you keep the value here, settling time, that is 4 times omega n damping factor upon periodic time, it is 2 pi by omega. Okay, so 4 by 2 pi, okay, 4 by 2 pi omega upon, okay, this you will get, and you will get omega n 1 minus omega is equal to omega n damping factor square. So this will get cancelled out. So you will get 2 upon 5 1 minus damping factor whole square under root on damping factor. Okay. So now you got the relationship. So 2 upon 5 and damping factor was how much the damping factor is? It comes out as 4.54. Okay. Sorry, 0.54. Let me go. 5 upon it will come out to be 0.5. Okay. You cross check it once. Okay. So 2 pi 1 minus 0.59 whole square upon 0.59. So from here, what you will get? 2 pi upon this will comes out to be 0.65 upon 0.59. So it will comes out to be. Okay. So from here, you will get the values. Okay. So likewise, there are few problems are there 9.10, 9.11. So you have a soft copy, and in the soft copy at the last these answers are given. So you can try to solve it and check whether you are getting a correct answer or not. Okay. So this covers your basic system model, including dynamic systems also. Uh, yeah. In next class, we will cover transfer functions. Okay. In next class, we will cover transfer function and what else is left. Yeah, Laplace transforms and these two things we will cover in our next class. Okay. So if you have any doubt, you can ask. Otherwise, okay. So Kalyan, I have shared the link for previous recording also. Okay. Hello. Hello. Uh, Pranav. Uh, so I think we can end our class here. Kalyan, Pranav, Geeta, are you there?
Yes, sir.
Okay. I think you might have left. Karthik.
Yes, sir, I'm there.
Okay. Okay. So we can end our class here.
Yes, sir. Yes, sir.
Okay. Okay. Thank you all.
Thank you,
Bye.
sir.